This is short video summary for week 6, which is internal flow or flow inside pipes or ducts and those type of geometries. As you can see, here we have the flow inside the pipe, and we recognize that we have two different regions. The first region, which we call it hydrodynamic entrance region, or sometimes we call it developing region, is the region we have boundary layers gradually forming and from top and bottom surfaces, and they reach each other at this point. And this level, this distance shows the hydrodynamic developing region distance. And after that, we are going to have fully developed region. If the flow is laminar, we can use this formula, which is 1/20 Reynolds number times diameter of the pipe, or hydraulic diameter of any geometry, to calculate the distance we have for the developing region. And as you can see, after reaching developing region, the flow pattern for the velocity is going to be constant. For the pipes, the Reynolds number formula is very similar to the flat surface. The only difference is going to be characteristic length, which is going to be diameter. And diameter, because it's a constant number, so for the pipes or ducts, we are going to have one Reynolds number. It's not going to be like a flat surface, which the characteristic length was the length of the surface, and gradually Reynolds number increased by increasing the surface length. So here I also introduced the Reynolds number for circular cross section in terms of mass flow rate. So if it is necessary to use mass flow rate, you can always convert mass flow rate, because mass flow rate is density cross sectional area times velocity, and that velocity, of course, is the average velocity or mean velocity, because as you can see here, we have velocity profile from 0 or no slip condition at the wall to the higher velocity at the center. So we usually use mean velocity. For more details, you can go back to your lecture notes. Usually, if Reynolds number for the pipe is less than 2,300, we consider laminar. Above 4,000, turbulent. Between that, it's going to be transitional, and above 10,000, we are 100% sure it's going to be fully turbulent. We can draw this similar arrangement for temperature. Basically, we have a constant temperature pipe, and we can draw thermal boundary layers. And you can see from top and bottom side, the thermal boundary layers gradually grow and reach each other. And the distance we have from the pipe for those thermal boundary layers to reach each other, we call it developing region for temperature, or thermal entrance region. And after that, it's going to be fully developed region. The formula for this distance, which is the developing region for temperature, is very similar to the hydrodynamic one. The only difference is we add Prandtl number there. So if the Prandtl number was bigger than 1, your developing region is going to be longer. If your Prandtl number was smaller than 1, your developing region for temperature is going to be shorter than hydrodynamic one. And this is for laminar cases. If it was turbulent, which is given here, temperature, developing region for temperature and hydrodynamic is going to be 10G. Okay, then we talked a little bit about mean or average temperature, and we talked, and I extracted the formula for this, because as you can see, we have temperature profile, but when we do the calculation, we prefer to have one temperature to represent the temperature of the fluid at that specific cross section. So we extracted some formulas, and if you are interested, please go back to lecture notes. Then we talked a little bit about pressure in the pipe, and we said at the beginning, because we have some resistance to enter the pipe, so definitely the pressure is going to be high. Gradually, this pressure going to reduce at the developing region. This reduction is a little bit sharper, and when we reach to the fully developed region, the reduction of the pressure is very linear, and as gradually this basically flow establishes and the pressure drops. But remember, we talked about this. If you wanted to draw the pressure drop against the distance, so delta P against the distance x, from developing region, this is going to be upward, because always pressure drop increases at the pipe. This is just pressure in the pipe. Okay. Then we talked about how the convective heat transfer coefficient, or the dimensionless form of that Nusselt number, is going to behave inside the pipe. Again, at the developing region, we have very sharp high number of H gradually decreases, and this is because of the boundary layer thickness. And when we reach to the fully developed region, interestingly, H and friction coefficient is a constant number, which is very interesting there. And another interesting aspect you can see here, for constant temperature and constant heat flux, here at fully developed region, you can see it's very similar and they overlap. So this is another interesting observation we can have from these graphs. Let's move on. Then we introduce two different conditions when we have a pipe with constant heat flux. Basically, we have a heater over the pipe, or constant surface temperature. If we had a constant heat flux, we extracted the formula for temperature. So it depends on the length, this x, where you want to find the temperature of the fluid inside the pipe with a constant heat flux, you can find the temperature there. For the case with constant surface temperature, it was a little bit complicated, because when we integrated, we got exponential equation, and you can see that the behavior of the temperature is exponential here. So one side we have very sharp reduction or increase, depends on the heating or cooling, and the other side is going to be much more slower change. So to have a fair calculation, we need to have some criteria to set, and that criteria. So by using this formula, we can calculate the temperature at any point inside the pipe when we have a constant surface temperature, and then get the number. If we needed to calculate H, later we need to get heat transfer rate. So heat transfer rate when we have a constant surface temperature is going to H times surface area times delta T ln. Basically, it is going to log mean temperature difference, and this is going to be much more fair temperature difference whenever we have a constant surface temperature. Then we introduce some formulas when we have fully developed laminar flow for the circular pipe. These are the different formulas. As you can see, it's a constant Nusselt number for constant heat flux. This is for constant temperature. And for other variations, we introduce other formulas. If it's fully developed, turbulent, smooth surface, we have some other formulas introduced. And depends on the condition of the question, you need to select the ones useful for you, because you are going to see some of them. For example, this one is Reynolds number must be above 10,000, and this one above 3 times 10 power 3 and less than 5 times 10 power 6. So different condition, different formula is generated. What if happens are we were investigating heat transfer for internal flow, but the geometry wasn't pipes like. What if they were like a duct? For those cases, we are going to use hydraulic diameter. Hydraulic diameter is introduced to have a diameter representing that geometry, which is going to be used inside our previous formulas introduced for circular cross-sectional area. And you can see hydraulic diameter is 4 cross-sectional area divided by wetted circumference. And try never to jump very fast when you find the geometry is not circular, because for some of the famous or very for some of the geometry with many application, we have some experimental results and formulas available. For example, for the rectangular geometry, depends on the ratio of the length to the height. We have Nusselt number values for constant temperature, constant heat flux, and if you're looking for friction factor, those formulas also given for isoscale triangle and ellipse. Even if these are provided. So if we have some studies working on these geometries and we have these results, it's better to use these results rather than using hydraulic diameter, because hydraulic diameter accuracy would be a little bit less than that, because these are the ones actually researched and investigated and supposed to have higher accuracy. And we talked about movie diagram, how it works. The x-axis was Reynolds number, y-axis was friction factor, and the other y-axis was our relative roughness. And by increasing roughness, our friction is going to increase. And as you can see, we have 3 regions. Fully rough region, which is going to be mainly related, the criteria for friction is going to be relative roughness, and this region, the transition region, which we have the effect of Reynolds number and relative roughness, and finally this region, which is going to be only the effect of Reynolds number and no effect of roughness. So if you are interested, again, you need to go back to the lecture notes and investigate a bit more the details about Moody diagram. Let's finish this summary video with the steps you need to go through when you have some type of question regarding this chapter. Usually you need to identify the geometry, if it's circle or other type of geometry, evaluate fluid properties and what temperature to use. Then you can select the density or viscosity and other fluid properties. Then you need to calculate the flow region, or basically calculate Reynolds number to find out if it's laminar or turbulent. And be careful if the geometry wasn't circle and we didn't have equations for that specific geometry, you need to use hydraulic diameter. Then we need to identify if the flow is developed or developing. This is extra steps you need to go in comparison to the external flow. And then you need to find out what type of heating condition we have. Is it a constant heat flux or constant temperature? This is another extra steps you need to do. And then investigating all these previous steps, you need to select the correlation for Nusselt number. This is going to be the major. Whenever you find Nusselt number, then you can calculate H. Whenever you had H, you can calculate Q dot. And you need to be careful for the pipe or surface with a constant temperature. Delta T inside the formula is going to be delta T, which is log mean temperature difference. Okay, thank you very much. See you next time.